over. In this video, we're going to be looking at functions. And out of this video, we'll be talking about functions as rules, as machines, as equations, as arrow diagrams, as tables in ordered pairs, and as graphs. Also, we'll look at sequences of as functions, also composition of functions, relations, and properties of relations. Okay. We'll talk about functions as rules. One can think of a function as a rule whereby one value is given. The function or the rule specifies the resulting value. Okay. Like in this situation here, let's say we want to guess the teacher's rule for the following responses. Okay, so if the student gives a number 1, the teacher responds with a number of 3. If a student gives 0 as a number, the teacher will respond with 0. For 4, the teacher responds with 12, and for 10, the teacher responds with 30. So looking at this, we can guess that we're multiplying the number that the student gives by 3. That's going to be 3 times n. So for n is 1, 3 times 1 is 3. For 0, 3 times 0 is 0. For 4, 4 times 3 is 12. And for 10, 10 times 3, which is 30. So 3 times n will be the rule that the teacher is using. Now in part B, the student gives the number 2, but the teacher responds with 5. The student gives a 3, the teacher responds with 7. For 5, the teacher responds with 11, and for 10, the teacher responds with 21. So here, we're doubling the original number and add 1 to it. So in other words, if a student gives 2, that means 2 times 2 will be 4 plus 1 will be 5. For 3, 3 times 2 is 6 plus 1 is 7. For 5, 2 times 5 will be 10 plus 1 is 11. And for 10, 2 times 10 is 20 plus 1 is 21. So we're doubling the original number and then adding 1, which is 2n plus 1. Now in this particular rule, if a student gives a 2, the teacher responds with 0. If the student gives a 2, the teacher responds with 0. For 7, the teacher responds with 1, and for 21, the teacher responds with 1. By looking at this particular rule here, we can guess that if n is an even number, like 2 and 4, they're even numbers, the answer is going to be 0. If the number is odd, like 7 or 21, the teacher is going to respond with the number 1. Okay? And keep in mind, there are other answers that are possible for this particular rule. Next, we'll look at functions as machines. Another way to think of a function is a machine. The machine always has an input and an output. And the machine will work according to the rule that is set. So, in this particular situation here, we're going to square the input. That means if we put in a 6, for example, and we want to square 6, that's 6 times 6, which will give us the output of 36. In this example, we have a function machine where it's adding 3 to the input to give us an output. Like in this case here, if we input the number 4, we're going to add 3 to the 4 to get 7. So that's f of 4 equals to 7. So for the function named f, what will happen if the numbers 0, 1, 3, and 6 are entered? Okay, so here, another way of writing the function machine is right like this in this expression. F of x is equal to x plus 3. So if x is 0, we add 0 plus 3. That's going to give us 3. If x is 1, that'd be 1 plus 3, which will give you 4. If x is 3, 3 plus 3 will give you 6. And if x is 6, 6 plus the 3 will give you 9. Okay. And we can write an equation to depict the rule in the previous example. If the input is x, the output is x plus 3. That is, f of x is equal to x plus 3. And as you can see, these are the values that we came up with using that function machine. Okay. A function from set A to set B is a correspondence from A to B in which each element of A is paired with one and only one element of B. So in this case here, the input, that's your domain. That's the set of all the inputs. That's your domain. And all the outputs represent the range, which is set B. Okay, is this input-output machine a function machine? And it's this: for any natural number input x, the machine outputs a number that is less than x. And the answer for that one will be no. And the reason for that is, let's say you input the number 10. The machine may output 9 since 9 is less than 10. But let's say you input 10 again. Then the machine may output another number like 3. And in this case, 3 is less than 10. Okay? So this would not be a function machine because you can input the same number and you might get different outputs. Alright, in this example, we have a high-end bicycle manufacturer incurring a daily fixed cost of $1,400 for overhead expenses and a cost of $500 per bike manufactured. Find the cost, which will be C of X, of manufacturing X bikes in a day. And let's say here that, of course, the cost of producing a single bike is $500. Because of that, the cost of producing X bikes is 500 times X. So it'll be $500X. Because of the fixed cost of $1,400 per day, the total cost, which will be C of X, in dollars of producing X bikes in a given day will be this particular function. C of X is equal to 500X plus 1,400. Now let's say that the manufacturer sells each bike for $700 and the profit or the loss in producing and selling X bikes in a day is P of X. And we want to find P of X in terms of X. Okay, so here, P of X will be this: 700 bikes, $700 per bike, X bikes, that's 700X, minus the cost of manufacturing X bikes in a given day, that's 500X plus 1,400. Notice that 500X plus 1,400 is in parentheses. Okay, so when you simplify this using the distributive property, you're going to have this 700X, bring that over. That minus sign will make the 500X minus 500X. And the minus sign makes the plus 1,400 minus 1,400. And then you combine your like terms. 700X minus the 500X, that will give you the 200X minus 1,400. So here, your profit or loss in producing and selling bikes in a day, which is P of X, that's going to be equal to 200X minus 1,400. Okay, we want to find the break-even point. That is the number of bikes, which is X, produced and sold, at which break-even occurs. So the break-even means to make neither a profit or a loss. So that means we need to find the number of bikes, which is X, to be produced so that P of X is equal to 0. That means no profit, no loss. You'll take that 200X minus 1,400, set that equal to 0. And then you're going to add 1,400 to both sides to get the 200X is equal to 1,400. then you have to divide both sides by 200 to get x is equal to 7. Okay, so if the manufacturer wants to break even, he will have to sell 7 bikes. Okay, anything less than 7 bikes will be a loss. Anything greater than 7 bikes will be a profit. We'll look at functions as arrow diagrams. Arrow diagrams can be used to determine whether a correspondence represents a function. On the left-hand side, you got 0, 1, 2, and 3, and then each of those numbers is paired with a single dot. And by the way, this should, let's say if I put some numbers here like 1, 4, 7, and 10. This would be a function because you can see 0 is only paired with 1, 1 is only paired with 4, 2 is only paired with 10, and 3 is only paired with 7. That means each number in the domain is paired with only one number in the range. On the right side, this one is not a function because if you see here, 3 is paired with two different numbers, 4 and 10. Now, if you have a number in the domain paired with two different numbers in the range, then that means that this particular diagram will not represent a function. Okay? Because you can only have one x value paired with only one y value, or one number or one element in the range paired with only one element in the range. I'm sorry, one element in the domain paired with one element in the range. Which, if any, of the figures exhibit a function from A to B? If a correspondence is a function from A to B, find the range of the function. Okay? This one on the left is not a function. Notice that 1 is paired with 2 and with 4. So that would not represent a function. The one in the middle is not a function. Well, here A is paired with 1 and C is paired with 2, but B is not paired with anything because there is no correspondence for B with something in the range. So that's not a function. This last one is, because X is only paired with A, Y is only paired with C, and Z is paired with B. Now D, it doesn't matter. It doesn't have to be paired with anything in the domain, okay? Because you have to have something from the domain paired with something in the range. Well, only one element in the range in order for it to be a function. Now, what's the range of that function? Here it's only going to be A, B, and C. The reason for that is A is paired with X, B is paired with Z, C is paired with Y. We don't include D because D is not paired with anything in the domain. Okay, here's more examples here. This also is a function because each name in the domain is paired with a last name in the range. And the one on the right side is also a function as well because each element in the domain is paired with only one element in the range. And the range here will be 1, 4, 7, and 10. And I forgot to mention the range over here will be Brown, Smith, and Doe. We'll look at functions as tables in ordered pairs. The L&B Lawn Service distributes the following fee schedule to their customers. It gives the price for mowing large lots given the number of acres in the lot. So here we can represent this as a table where 1 is with $50, 2 is $85, 3 acres is $120, 4 acres is $155, 5 acres is $190. Or we can represent that as ordered pairs. 1 is paired with 50, so that'd be $1, $50. And then for 2, And 85, that'll be 2 comma 85, 3 comma 120, 4 comma 155, and 5 comma 190. So we can represent functions as either a table or either in a set of ordered pairs. Which of the following sets of ordered pairs represents functions? If a set represents a function, give its domain and range. If it does not, explain why. Let's look at this one. We got the set with the ordered pairs 1, 2, 1, 3, 2, 3, and 3, 4. In this case, it's not a function because, as you can see, the input, which is your 1, has two different outputs, the 2 and the 3. So this set is not a function. B is a function because if you look at your first order pairs, which is your inputs, they're different. They're only paired with one element in the range. So here the function has a domain, which is 1, 2, 3, 4. The range is 1/2, 1/3, 1/4, 1/5. Now you can think of this as x and this is y. The first number is your x and the second number is y. And the function and the domain will be the set of all x values, and the y and your range will be the set of all y values. Also 1, 0, 2, 0, 3, 0, 4, 4. This is a function because only one x value is paired with only one y value. Even though the 1, 2, and the 3 is paired with 0, that's still going to be a function because you're only looking at the x coordinates here. And the domain here will be those x coordinates 1, 2, 3, 4. The range will be the set of all y coordinates, just 0 and 4. And part D, the set of all ordered pairs A, B, such that A is an element of the natural numbers and B is equal to 2 times A. That would be a function because the domain there is just all your natural numbers. The range is just going to be the set of all even numbers 2 times whatever A is. We can look at functions as graphs. Graphs are probably the most commonly known ways of representing functions here. Here we got a graph of L&B lawn service. The horizontal axis represents the acres and lot. The vertical axis represents the cost in dollars. And notice that they plotted those points on a coordinate plane. You can see that this would all form a straight line. So that would be a function. Okay. Now explain why a telephone company would not set rates for telephone calls as depicted on the graph. All right, and here's the reason why. The graph does not depict a function. For example, a customer could be charged either 50 cents or 85 cents for a 2-minute call. Okay, here's 2 minutes right here. That's the number of minutes. Here, he could be charged either 50 cents or 85 cents. Okay? So, not every input has a unique output. So, this would not represent a function. We can look at sequences as functions as well. We talked about arithmetic and geometric sequences earlier in the course. Arithmetic, geometric, and other sequences can be thought of as functions whose inputs are natural numbers and whose outputs are the terms of a particular sequence. Like, for example, the arithmetic sequence 2, 4, 6, 8, and so on, whose nth term is 2n, can be described as a function from the set of natural numbers to the set of even numbers. Using the rule f of n is equal to 2 times n, where n is a natural number and f of n stands for the value of the nth term. Look at this example. If f of n denotes the nth term of the sequence, find f of n in terms of n for each of the following. An arithmetic sequence whose first term is 3 and whose difference is 3. Okay, in this case here, it would be f of n is equal to 3 times n, and n is going to be a natural number. Okay, because the first term is going to be 3, and if the difference is 3, so that means 3 plus another 3, that's 6, then 9, then 12, 15, 18, and so on. So it'll be 3 times n. Part B, a geometric sequence whose first term is 3 and whose ratio is 3. So in this case here, it will be 3 raised to the power of n. As that ratio is 3, and it's a geometric sequence, so it's got to be an exponent involved in it. So it'll be 3 to the nth power, and n is the natural number. We can look at sums of sequences as functions, like the sum of n terms in an arithmetic sequence, with the first term being a sub 1 and the nth term, a sub n, is given by this. The quantity of a1 plus a sub n divided by 2, and that whole thing is multiplied by n. Like in this example here. Let's say we want to find the sum of the first 100 terms of the following arithmetic sequence. In this case here, we got 3, 7, 11, 15, 19, and so on. Well, first of all, we find out what the common difference is. We can subtract any two consecutive numbers here. 7 minus 3 will give us 4. So the common difference there is 4. So the sum will be 100 times 3 plus 100 minus 1 divided by 4 halves, which is going to be 498. Also, we can look at the sum of the n terms in a geometric sequence whose first term is a sub 1 and whose ratio is, where r is not equal to 1, that's going to be this. S is equal to a sub 1 times 1 minus r to the n divided by 1 minus r. So in this case here, if we want to find the first 10 terms of the geometric sequence, or the sum of the first 10 terms, the ratio here is going to be negative 1/2, because you take negative 3 halves divided by, it should be divided by 3. Negative 3 halves divided by 3, which will be negative 1/2. And then you're going to use that particular formula where a sub 1, that's your 3, that's the first term, times the numerator is 1 minus r over n, 1 minus negative 1/2, and we're finding the first 10 terms, that's to the 10th power, divided by 1 minus r, or 1 minus the negative 1/2. And if you simplified all this, you would get 1023 over 512. Okay, next we'll look at compositions of functions. If 2 is entered in the top machine, then f of 2 is going to be 6. Let's look at this one. We got two machines. One is for f of x and another one is g of x. F of x is represented by x plus 4. We're entering the 2 in the top machine. So that means we add 4 to that 2. That would give us 6. And then the number 6 is going to be entered into the second machine of g of x, which is going to be 2 times x. So if this is 6 from the f of x, then we put that value into the g of x function, 2 times 6. That would give us 12. What this function machine does, it illustrates what we call the composition of functions. So here you can see that the range of f becomes the domain of g. Okay, because that's your domain that you start off with, and you end up with a range. Now that range is now going to be the domain for g. Alright, now let's look at this situation here. If f of x is equal to 2x plus 3 and g of x is equal to x minus 3, find the following. Now this is the illustration of how they write the composition of functions here. F circle g means the composition of f with g at x is equal to 3. So x is equal to 3 here in this case. And another way of writing this would be this, f of g of 3. And inside the parentheses is g of 3. Well, g of x is equal to x minus 3. So in place of this x, we're going to put 3 in its place. So it'll be f of 3 minus 3. Well, 3 minus 3 is going to be 0, so we'll be evaluating f of 0. Now, f of x is 2x plus 3. And x is 0, so in place of this x, we're going to put 0 in its place. So it'll be 2 times 0, which is 0, plus 3, which is going to give you 3. Okay. So we replace our x value in g of x, and whatever that is going to be replaced for x in the f of x function. Now, the opposite, or the other way around, g circle f, or the composition of g with f of 3, is going to be this, g of f of 3. Inside the parentheses is f of 3. You first replace your x with 3 in the f of x function. So now you got 2 times 3, which is 6, plus that 3 will give you 9, so you're going to be evaluating g of 9. And g of x is x minus 3, so you'll replace the x with the 9, so it'll be 9 minus 3, which will give you 6. Okay? So notice the difference between the composition of f with g and the composition of g with f. Now, let's say they want to find the composition of f with g of x. Okay, so now, f of g of x means the composition of f with g of x. So, here in this case here, you take your g of x, replace it for x in the f of x equation, which would be 2 times g of x plus 3. But what's g of x equal to? X minus 3. So that g of x, you're going to replace that with the x minus 3. So here you have 2 times the quantity x minus 3 plus 3. Simplify this, you're going to get 2 times x, which is 2x. Then 2 times the minus 3 will be minus 6 plus 3. Combine like terms, minus 6 plus 3 will give you minus 3. So you'll end up with 2x minus 3 as the final answer, or for the composition of f with g of x. Now, we want the composition of g with f of x, which is represented by g of f of x. Well, g of x is x minus 3. That x is going to be replaced with this f of x. So now you have f of x minus 3. But what's f of x in this case? 2x minus 3. So let's replace this f of x with 2x minus 3. So now you get 2x minus 3 plus 3. Simplify, adding 3 and subtracting 3 is the same as adding 0, so you're left with 2x, which is the answer to the composition of g with f of x. Alright, next is relations. A relation from set A to set B is the correspondence between elements of A and elements of B, but unlike functions, we do not require that each element of A be paired with one and only one element of B. So any set of ordered pairs is a relation. Now, keep in mind that every function is a relation. However, not every relation is a function. Consider this relation is a sister of, in quotes. The figure illustrates this relation among children on a playground, with letters A through J representing the children's name. An arrow from I to J indicates that I is a sister of J. Notice that arrows from F to G and from G to F, which indicate that F is a sister of G and G is a sister of F. So that means that F and G are both girls. On the other hand, the absence of an arrow from J to I implies that J is not a sister of I, as you can see here. So I is a girl and J is a boy. Another way to show the relation is a sister of is to write the relation A is the sister of B as an ordered pair, A comma B. So the relation can be written as the set, which is this right here, A comma B, A comma C, A comma D, C comma A, C comma B, C comma D, D comma A, D comma B, D comma C, F comma G, F, G comma F, and I comma J. And what that is a subset of this right here. And if you recall, we did talk about cross products. Okay, given any two sets A and B, any two sets, excuse me, any two sets A and B, a relation from A to B is a subset of A cross B. That is, R is a relation from set A to set B if and only if R is a subset of A cross B. And then you have properties of relations. One of them is the reflexive property, which is a relation R on a set X is reflexive if and only if for every element A is an element of X, A is related to A. That is, for every A, an element of X, A comma A is an element of R. And then the symmetric property is a relation R is on the set X is symmetric if and only if for all elements A and B in X, wherever A is related to B, then B is related to A. That is, if A comma B is an element of R, then B comma A is also an element of R. And then last is the transitive property, where a relation R on a set X is transitive if and only if for all elements A, B, and C of X, wherever A is related to B and B is related to C, then A is related to C. In other words, if A comma B is in R and B comma C is in R, then A comma C must be in R. And keep in mind that A, B, and C do not have to be different. An equivalence relation is any relation that satisfies the reflexive, symmetric, and transitive properties. So those three properties that I mentioned, if that relation satisfies all three of those properties, then you have a equivalence relation. And that will conclude this particular video on functions.